Oh, sorry for the trouble today. I hope to make this video thing work. So if you could please turn to page 2 of the second handout that I just emailed you guys last night. So what we are trying to do in our in this in our attempt to overcome all those challenges in solid state NMR, we are trying to achieve three things. So first is to remove the orientation dependence of chemical shifts, or CSA, and we are gonna achieve that by the so-called magic angle spinning. So when you are running your experiment, you spin the sample really fast along this angle, and this angle forms this direction forms an angle with the external field at that so-called magic angle is about 57 degrees, as you can see on the diagram on the top right. So if you do that, usually like you can spin it somewhere like several kilohertz or up to like a tenth of a kilohertz. So that's one thing, and that will remove the chemical shift anisotropy. And the next thing, what we want to achieve is to remove some Doppler coupling. And the easiest one to remove is the Doppler coupling between proton and carbon. And so I say like, or other X. So in the NMR terminology, X means all the nuclei except proton. So proton is proton. It's in a special category. Everything else is X. So like a phosphorus is an X, and our example on the next page is a phosphorus spectrum. So to remove the strong Doppler coupling between, for example, proton and carbon, by the so-called high power decoupling pulse. So the way it works is when you detect on X, or for example carbon, you send a pulse on proton, and that will remove the Doppler coupling. And you know, this is if you are familiar with the carbon spectrum on solution, this is exactly the same thing. You pulse on the proton channel when you acquire carbon signal. The only slight difference here is that you need to apply a very high power, because you need to remove a very strong coupling, which is the Doppler coupling, which is much stronger than the J coupling. So J coupling is somewhere around 100 hertz, and Doppler coupling is like a tenth of a kilohertz. So to overcome that, you need a strong decoupling pulse. So high power decoupling, and this is to decouple, for example, proton carbon. And yeah, this kind of a coupling is sometimes called heteronuclear decoupling. Heteronuclear, when I say heteronuclear, I mean the partners of the coupling are different nuclei. So then there's also like homogeneous, homonuclear type of coupling. So which is proton. That's homonuclear Doppler coupling. That is more difficult to do. So the reason being, when you detect carbon, and you can decouple on proton because protons are in a different frequency. So so you 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 can't pulse and detect the same frequency at the same time because the pulse is so much stronger than the signal. And if you if you detect on carbon and you pulse on carbon, the pulse will completely overwhelm the signal. Um, so, uh, however, you can pulse proton. You can pulse proton and detect carbon, so that's workable. So this is why it's kind of difficult to remove the proton-proton dipole coupling, because you can't pulse and detect on proton at the same time. So this means that proton solid state NMR is not really useful. So we'll mainly focus on the X nuclei, like carbon, silicon, or like phosphorus, and we're gonna detect those and decouple on proton. So that's what we're gonna do. So that's our second objective. And the third objective is signal intensity improvement. Because if we're going to rely on the carbon information, we know carbon is only 1%. It's not a lot of signal, so we need some ways to get a stronger signal. And the technique that can achieve this is called cross polarization. Polarization means excitation. So and here it's cross polarization, which means that like let's say if you want to detect carbon, what you're going to do is actually first you are going to excite proton first, and then you're going to transfer signal from proton to carbon, and that's called cross polarization. So it almost sounds like cross pollination. It's a very similar idea. Um, so that's our three objectives. So if we turn the page to the next slide, here's an example of a phosphorus spectrum. So the blue one is without sample spinning, and you see this pattern here, and try to recall what name this kind of pattern is. And then the red one is the with spinning, and the spinning speed is 1090 hertz, so around 1000 rounds per second. And you see there are a lot of sharp peaks. And so when the peaks are sharper, you begin to have a chemical resolution. And so there are a number of sharp peaks, and so in fact only one of them is real, and so that's where the center band is, and all the other ones are called spinning side bands, and that's marked with asterisks. Those are, you see, all these peaks are regularly spaced, which is no surprise, because their distance is the multiples of spinning speed. So you can easily recognize the position. You can easily recognize the side, which are side bands, by the peak position.